Hello and welcome that contain underpinning knowledge. There are two hydrostatic presentations. The first is Introduction to Hydrostatics, outlining various definitions, pressure, etc., units used and characteristics of fluids. And the second hydrostatics presentation considers pressure in fluids due to self-weight of the fluid and the formula ρgh. We will be using a similar formula in this presentation, but using the notation ρgz. Then there is a hydrodynamics presentation related to Bernoulli's equation, which is quite analogous to the steady flow energy equation we're going to consider in this presentation. The presentation considered essential to review is the non-flow energy equation, as that relates to closed thermodynamic systems and has much underpinning knowledge for our steady flow energy equation presentation here. Here's a presentation overview. We commence with a brief introduction, defining terms of thermodynamics, working substance, enclosed and open systems. Next we consider the properties of mass, volume, pressure, temperature. Then we consider forms of energy, such as heat energy, work done, kinetic energy, potential energy. We then consider open systems and the additional form of energy, termed flow work. Then we consider an energy balance from which we can derive our steady flow energy equation, outlined here in its general form. We consider rate quantities, heat transfer rate, work done rate, mass flow rate. Then we have two examples. Example 1, have to calculate the work done per kilogram, lowercase w, and the associated power. And example 2, we have to find the heat transfer, symbol capital Q. Finally, there are some tutorial questions for you to attempt at your own pace. And here are the approximate start times to the various sections contained within the presentation, hopefully to aid your ease of access through the presentation, but please note all times are rounded to the nearest minute. Here's our introduction to the presentation. We define the term thermodynamics. Thermodynamics may be defined as the branch of physical science which considers the various forms of energy and the related properties of matter, particularly the laws of transformation of heat into other forms of energy. To meet society's modern day requirements, an array of engineering plant still used, for example turbines, compressors, reciprocating engines, boilers, condensers and refrigerators. Each of these items makes use of the behavior of a fluid as it is heated, cooled, expanded or compressed. The design and operation of such equipment requires an understanding of the energy laws just as much as an understanding of the mechanical laws. This presentation endeavours to explain in general terms the principles involved. Working substance and systems. Heat engines are devices in which energy transfers by heating are transformed into energy transfers by working. Heat engines require a working substance, fluid, liquid, gas or vapour, in which energy is absorbed, stored and released as required. Examples of working substances are steam, used in a steam turbine, air, used in an air compressor, petrol mixture, used in a car engine, freon, used in a refrigerator system. Working substance and systems continued. The problems involving transformation of energy are solved using systems concepts, and a system being defined as a region in space containing a fixed amount of matter enclosed by specified boundaries which may be real or imaginary. There are two categories of system which are open and closed systems. Let's overview systems. So as stated previously, systems may be considered either closed or open. Let's review closed systems. A closed system, as shown within the power station of figure 1, is figure 1 here, diagrammatically showing the power station, where there is no exchange of matter with the surroundings. Here, the overall performance of a thermal power station relates the energy output, electrical work, and here, to the energy input stored in the fuel. This type of system relates to the non-flow energy equation, which is outlined in a previous presentation. Let's consider an open system. An open system is shown in figure 2, diagrammatically shows a turbine, in which there is transfer of matter across the boundary, in addition to any energy transfers. In this case, the system defined by a boundary which encloses a fixed volume rather than a fixed mass. Here's the boundary, also referred to as the control surface. Open system continues. The volume is called the control volume, and the surfaces across which the energy is transferred and matter passes are called control surfaces. Such a system boundary may be used to investigate reasons for poor performance. Thus, each item in a power station would require to be studied, and if the item is, say, a turbine, the machine casing would form the system boundary, as shown within figure 2. Figure 2 repeated for convenience, again showing the system boundary or control surface. Let's consider properties. To calculate energy changes occurring in a system or a working fluid, the behaviour must be described in terms of its properties or characteristics. Characteristics of a motor car, such as acceleration, maximum speed, turning radius, etc., are all essentially mechanical related to a particular vehicle. In the case of a power station, the properties are thermodynamic and, unlike the mechanical examples, are often not directly measurable. Thermodynamic state of a system or substance is defined by important properties of independent quantities, as will be stated on the following slides. Properties continued. So firstly, the property of mass, symbol lowercase m. Mass is the quantity of matter in a system or substance. Mass has the SI unit of the kilogram, and that's a base unit. Let's consider volume, uppercase V, and specific volume, which I'm denoting as an italic lowercase v in this presentation. So volume is the physical space occupied by a given mass of substance. Specific volume is the physical space occupied by 1 kilogram of a substance. Thus, for a mass m of a substance, the volume uppercase V can be calculated from equation 1, where V is equal to the mass m multiplied by the specific volume, lowercase italic v. That's called equation 1 purely for reference. The SI unit of volume, capital V, is the meter cubed, and the SI unit of specific volume, italic lowercase v, is the meter cubed per kilogram. And of course that can be written as a meter cubed kilogram to the negative 1. Let's consider pressure, denoted as lowercase p. So pressure is the force per unit area exerted by a fluid. In the case of a gas, force, capital F, is due to the impact of gas molecules on the surface of the container, so it is a surface force. In the case of liquids, the force is due to the weight of the body of the liquid, so it is a body force on the resisting or supporting surface. So average pressure, lowercase p, defined as the force acting, F, divided by the area resisting, capital A. Call that equation 2 for reference. The SI unit of pressure is measured in Newton meters to negative 2, or alternatively measured in pascals. Note for reference that 1 bar is 10 to the 5 pascals, and 1 pascal is 1 Newton per meter squared. We've reviewed in detail these units in our Introduction to Hydrostatics presentation. Properties continued. Here's actually a recap slide from our previous presentation where we outline the difference between absolute pressure, which is measured from the datum of zero pressure, and gauge pressure, which is measured in relation to atmospheric pressure, which is approximately 1 bar. So gauge pressure is equal to absolute pressure minus atmospheric pressure. Again, these properties are considered in the previous hydrostatics presentation. Let's consider temperature in terms of the arbitrary scale Celsius degrees C. So temperature is a measure of the ability of a system to transfer heat to other bodies. Temperature is a measure of the kinetic energy contained by the molecules. If heat energy flow is considered analogous to electrical energy flow, i.e. current, then the temperature can be usefully thought of as the thermal potential and analogous to the electrical potential, i.e. the voltage. The temperature scale in general use is the Celsius scale based on the ice point, atmospheric pressure, and the steam boiling point of water, atmospheric pressure. Such temperatures are stated in degrees Celsius, denoted here. Let's consider the thermodynamic temperature. This is the absolute scale, Kelvin scale. This is a property of a system measured above absolute zero. Absolute temperature is measured in degree Kelvin, denoted by the symbol uppercase K. The relationship between the arbitrary scale, Celsius scale, and the absolute scale, Kelvin, is shown in the sketch on the right hand side here. On the Celsius scale, water freezes at 0 degrees C and it boils at 100 degrees C. On the Kelvin scale, water freezes at 273 K and boils at 373 K. That's because the Kelvin scale commences from 0 K, absolute zero, would be approximately negative 273 degrees C. So what we do note between the two scales is that the increments are the same. 1 degree C is equivalent to 1 K, and that's very useful to know. Illustration below shows conversions. If you want a temperature in terms of Kelvin, or given a temperature in degrees C, and you actually add 273.15 to determine the K value. So for example, 573.15 K is 300 degrees C. Similarly, if you want to find the temperature in degrees C, the arbitrary scale, you're given a temperature in Kelvin, you now subtract 273.15 to find a temperature in degrees C. So for example, 100 degrees C is 373.15 K. Let's now consider energy and its various forms. So energy is the capacity to perform useful work and can appear in different forms which are capable of being converted between the various forms. The total amount of energy possessed by a system is difficult to determine in absolute terms. However, it is the change of energy that is of major interest. The main forms of energy applicable to thermodynamics are heat, work, kinetic energy, and potential energy. These will be reviewed on the following slides. Energy and its forms continued. Let's consider heat energy, symbol uppercase Q. So heat is energy appearing at the boundary of the system due to a temperature difference between the system and its surroundings. The important point to note is that the energy form is only heat when it is in transition between the system and the surroundings. The system does not contain heat, it only contains energy. Due to the directional nature of the transfer, the following sign convention is used. So heat into the system is denoted as positive, and heat out of the system is denoted as negative. That's the same notation we used in our previous presentation related to the non-flow energy equation. The SI unit of energy is the joule, symbol uppercase J, and SI multiples in common usage include the kilojoule, denoted here, and the megajoule, denoted here. For your reference, it's important to be aware that heat energy can be transferred in 3 different ways: by conduction, convection, and thermal radiation. There's a previous presentation related to methods of heat transfer for your reference. Energy and its forms continued. Let's consider work energy, symbol uppercase W. So work is energy appearing at the boundary of the system, equivalent to the displacement of the boundary by the action of a force. Work may appear as an actual displacement, such as a piston moving in a cylinder, or alternatively as a torque applied to a shaft. The following sign convention should be adhered to when considering work. Work out of the system is positive, and work into the system is negative. Again, the notation we used in our previous non-flow energy equation presentation. The SI unit of work is the Newton meter, more commonly referred to as the joule, symbol uppercase J, and again multiples in common use, and the kilojoule and the megajoule. Energy and its forms continued. Let's consider kinetic energy, KE. Kinetic energy is possessed by the system due to motion of its mass center. The energy value is given using the definition from mechanics, so KE is equal to a half mv squared, or mv squared divided by 2, and that's equation 3 for reference. Note that M denotes the mass of the fluid, that would be in kilograms, and V is the fluid's mean velocity, that would be in meters per second, or of course meters second to -1. And the SI unit of kinetic energy is the joule, multiples kilojoule, megajoule. Energy and its forms continued. Potential energy, PE. The potential energy is possessed by the system due to virtue of its elevation above a specified datum. The energy value is given by the definition from mechanics. PE is equal to mgz. We use the notation mgh in previous presentations, but z is being used here for height above a datum, and that's labelled equation 4 for reference. Again, mass m being kilograms, and height z being meters. The SI unit of potential energy, of course, is joule. Typical multiples again, kilojoules, megajoules. Let's consider energy in open systems. So in our previous presentation, the non-flow energy equation, acronym SFEE, was derived for closed systems. In this presentation, the steady flow energy equation, acronym SFEE for short, will be generated for open systems, as illustrated in figure 3. An open system analysis considers transfer of energy contained in the fluid passing through the system during its operation. Energy in open systems continued. Thus, in addition to heat Q and work W transfers, as we previously considered in the non-flow energy equation, the following fluid energy terms are also considered in an open system: internal energy, symbol uppercase U; kinetic energy, Ke, formula half mv squared; potential energy, Pe, formula mgz; an additional form of energy referred to as flow work, which is the pressure multiplied by the specific volume. Open systems continued. So flow work is an additional energy term associated with flowing fluids, representing work done on the fluid entering the system and fluid leaving the system. Consider the fluid flowing in a pipe of cross-sectional area uppercase A, with the mass m occupying length x, which is just about to enter the system, as shown in figure 4. Here's figure 4. For the mass to enter, a force F must act on the imaginary diaphragm labelled as YY in figure 4 here, to overcome the resistance offered by the system. Open systems continued. Just repeated figure 4 here for convenience. So this process effectively provides work input to the system. Thus, work done is the force F multiplied by dimension x, labelled here on the diagram. The force F is applied by the pressure P, here, acting over the area A at the front of section YY, the cross-sectional area through YY. So work done is equal to P pressure multiplied by A area multiplied by distance x. But note that A multiplied by x is actually volume V of the displaced fluid. So we can write work done uppercase W as pressure lowercase p multiplied by the volume uppercase V. And that's considered to be the flow work done on the fluid, which is an additional energy term to consider. Notice in figure 3, the symbol E here relates to the energy in the system. E1 is the energy before the system commences operation. E2 is the energy that would be in the system after the system is shut down. But often the system does not accumulate mass or energy, so the E terms are often ignored from the final equation developed. We'll outline this characteristic on the following slides. Let's consider the energy balance. So applying the energy balance to an open system produces the following equation. We have on the left hand side of the equation, the input side, we have the initial energy in the fluid added to the flow work done on the fluid, added to the kinetic energy, the potential energy, to the heat into the system. And also we add the term E1, which is the original energy in the system before commencement of the process. And on the right hand side, U2 is the energy in the fluid output, flow work output, kinetic energy output, potential energy output, and work done by the system. We then have the E2, which is the final energy in the system when the process is complete. Rearranging produces the following equation. So now here on the left hand side we have Q minus W, subtracted W from both sides of the equation, and that's equal to U2 plus P2V2. Then we subtracted U1 plus P1V1 from both sides of the equation. We then add Ke2 minus Ke1, to Ke1 from both sides. Then we add P2 minus P1, subtracted P1 from both sides. Finally we add E2 minus E1, subtracting E1 from both sides of the equation. In many flow situations, the changes of Ke, Pe and E may be considered negligible, but the change in flow work will be significant. Hence, it is convenient to group flow work and internal energy terms together into a single energy term relevant to flowing fluids. Energy balance continued, so this combined term is known as enthalpy. Symbol uppercase H denotes the enthalpy possessed by the total mass, and lowercase h denotes the specific enthalpy possessed by a unit mass per kilogram. Uppercase H is equal to the mass multiplied by the specific enthalpy, referred to as equation 5 for reference. Lowercase h is equal to lowercase u, the internal energy per kilogram, added to the flow work per kilogram, labelled as equation 6 for reference. So uppercase h, enthalpy of the total mass, is the total internal energy of the fluid added to the total flow work done on the fluid. That's equation 7 for reference. So substituting h for u plus pv in the previous equation, we'll substitute h2 here, h1 here, but changing this bracket here to h2 minus h1. That's now labelled as equation 8, and this is often termed the general energy equation. Energy balance continued, so note, on consideration of equation 8 on the previous slide, the system energy can now be changed by an alteration in the fluid energy in addition to the heat and work as previously considered within the non-flow energy equation, our previous presentation. From the non-flow energy equation presentation, we're going to use the same notation relating to heat and work energy. So heat supply to the system is positive, work out of the system is positive. Conversely, heat rejected from the system will be negative, and work input to the system will be negative. Same notation used for the non-flow energy equation. Energy balance continued. Many industrial flow situations can be considered as steady state in nature. In other words, the fluid mass flow rate does not vary with time and the system does not accumulate mass or energy. So often within the analysis, the terms E2 minus E1 can be ignored, as E2 minus E1 is 0. No change in the overall initial or final energy of the system. In such cases, equation 8 simplifies to this equation shown here, labelled as 9 for reference, which is often known as the steady flow energy equation, SFEE. Equation 10 below shows an alternative form of the steady flow energy equation in terms of specific energy, what I sometimes refer to as a specific steady flow energy equation, and thus all the terms are now per kilogram. Notice the change in symbols, uppercase symbols used in equation 9, but lowercase symbols used in equation 10. So summary of our open systems analysis. In open systems, as diagrammatically shown in figure 5 below, mass is transferred across the boundary, and for steady flow conditions, the mass flow rate, m dot, across the boundary must remain constant. However, both heat, symbol Q, work, symbol W, can cross the system boundary. Diagram shows heat into the system, crossing the boundary, and work out of the system, again crossing the boundary. But the mass flow rate of fluid in and fluid out would be the same. Let's consider rate quantities. It should be noted that many practical situations involve time rates of quantities such as heat transfer rates, working rates, mass flow rates. These are shown in equation 11 here. Q dot is the heat transfer rate, having the unit of the joule per second or watt. The work transfer rate, W dot, unit shown here. And the mass flow rate, M dot, having a unit of the kilogram per second. Rate quantities continued. Here's equation 11 repeated for convenience, showing the full nomenclature and units used. Rate quantities continued. Figure 6 here shows a steady flow energy system. At the inlet we have mass flow rate labelled as M1 dot. We have the velocity of the fluid. We have the height of the inlet to some specified datum. And at the outlet, location 2, we show mass flow rate m dot 2, although for a steady flow system, m dot 1 and m dot 2 would be the same. We have the velocity of the fluid at the outlet, and we have the location of the outlet from the data. Notice across the system boundary we have the heat energy in, Q into the system, heat supplied to the system, and we have work out the system, that's work done by the system. Let's consider mass flow rate, m dot. So the mass flow rate can be calculated from knowledge of the flow velocity, that dimensions, and the fluid properties at the control surfaces. So there's m dot, here's the area, calculated from the diameter of the pipe, and here's the specific volume, lowercase italic v. So considering volume flow rate, v dot, which will be in meters cubed per second, in the duct, this can be calculated using either of equations 12, shown on this slide, or 13, shown on the next slide. Here's equation 12, V dot is equal to M dot multiplied by specific volume, as equation 12. Note the unit for M dot, mass flow rate. and unit for a specific volume. This is equation 13, calculating the volume flow rate, this time using the mean velocity of the fluid multiplied by the area of the duct, mean velocity having the unit of meter per second, cross-sectional area of the duct having the unit of meter squared. Thus equating equations 12 on the previous slide and 13 on this slide produces the following: mass flow rate multiplied by specific volume is equal to the velocity multiplied by the cross-sectional area, and we simply rearrange mass flow rate m dot is VA divided by specific volume, equation 14. And the power output, E, from the system is calculated from the product of mass flow rate, m dot, and the specific work done, lowercase w, in joules per kilogram, by the system. So output power is m dot multiplied by lowercase w. Equation 15 for reference. Let's consider application of the steady flow energy equation. Here's example 1. A compressor of an industrial refrigeration unit has a fluid entering the system with a specific enthalpy of 360 kilojoules per kilogram and leaving the system with an enthalpy of 440 kilojoules per kilogram through a pipe of 1250 millimeters above the inlet. Assuming an adiabatic process, in other words, no heat transfer to or from the system, and that the change in kinetic energy is negligible, we've got to determine the work done and state if the work is in or out of the system. Furthermore, if the fluid's mass flow rate is 15 kilograms per hour, we've got to determine the associated power. A note from the information stated, the outlet pipe is 1250 millimeters above the inlet, so for calculation purposes the height of the inlet above the datum Z1 will be 0 and the height of the outlet above the datum Z2 will be 1.25 meters. And here's a few hints for the solution of example 1. Initially we will consider the specific form of the steady flow energy equation shown here, and we have to calculate the work done. We're told in the question it's an adiabatic process. In this case there will be no Q value, and we're also told that the kinetic energy is negligible, so we can ignore this term here from the equation. Once we've found the work done from the steady flow energy equation, we can then find the power required, P, knowing the mass flow rate given in the question and having calculated the work done per kilogram above. Just note that the mass flow rate given in the question is actually in kilograms per hour, and we need to calculate that in terms of kilograms per second. So I'd encourage you to start the presentation and attempt example 1, but the full work solution is shown on the following slides. So example 1, here's the commencement of the solution. As always, the first thing we do is to extract the information from the question. We're informed it's an adiabatic process, so that means the heat energy, simple lowercase q here, is 0. There's no heat in or out of the system. We have to calculate the work done per kilogram, specific work done. We're given in the question the specific input enthalpy, that's H1, 360 kilojoules per kilogram. Notice it's kilojoules here. And we're given the specific output enthalpy, H2, is 440 kilojoules per kilogram. We're informed that the change in kinetic energy is negligible, so velocity at inlet V1 assumed to be 0, velocity at outlet V2 assumed to be 0. We're informed that the outlet is through a pipe that's 1250 millimeters above the inlet. So if we take our datum at the lowest point in the system, that means Z1 would be 0, that's the inlet pipe, but the height of Z2, the outlet pipe, will be 1.25 meters, converting our millimeters to meters. We need to be careful with the mass flow rate, m dot, actually given in the question as 15 kilograms per hour, so we need to convert 15 kilograms per hour into kilograms per second. I'm using my unity bracket here, so 1 hour is 3,600 seconds. So 15 kilograms per hour becomes 1 upon 240 kilograms per second. I've actually written this as 240 to the negative 1 kilograms per second. Just be careful of the conversion. Remember, these are cancelling unity brackets, so hours on the bottom here cancels with the hours on the top to leave us with kilograms per second. There's a separate presentation related to the use of unity brackets for your reference. So that's the information extracted from the question. Now we can apply the specific form of the steady flow energy equation and solve for the work done. Example 1, solution continued. So part 1, as I've labelled it here, we're considering the specific form of the steady flow energy equation shown here on our slide. And of course from the question we know that there's no heat energy input or output to the system because it's an adiabatic process, and the change in kinetic energy is negligible, so the K energy is considered 0. So rearranging the equation for lowercase w, the specific work done, we end up with this expression. So in other words, we've added w to both sides of the equation, subtracted the enthalpy terms from both sides, subtracted the potential energy terms from both sides of the equation. And now simply insert the output enthalpy value given in the question, the input enthalpy value. Notice that they're in kilojoules in the question, kilojoules here. So that's my times 10 to the 3. Then we state the outlet height from our datum, and the inlet height is 0. Notice that the enthalpy term is 80 times 10 to the 3 joules per kilogram. And note how small the potential energy term is in comparison with the enthalpy terms. So essentially the potential energy terms are negligible in this case. So evaluating for W, it's essentially negative 80,000 joules per kilogram. Note from our sign convention, negative means work input to the system, so hence the work input to the system, W, is approximately 80 kilojoules per kilogram. This solution highlights the need to be aware that some values are given in kilojoules and some are in joules, so be very careful when you're calculating the answer that you do account for any prefixes that are stated in the question. In example 1, solution continued. I've just repeated our calculation for the mass flow rate here purely for reference to show the value of m dot. So step 2, as I've labelled this in my solution, we're calculating now the power. That's the mass flow rate m dot multiplied by the specific work done from our previous slide. Inserting the values, mass flow rate shown above, approximately 80,000 joules per kilogram for our specific work done. Hence our power works out to be 333.3 recurring joules per second, or 333.3 watts. That's the solution to example 1. Here's a second example of applying the steady flow energy equation. This is example 2. An open system working in steady flow receives a fluid of mass flow rate 9 ton per hour and having the following properties. Inlet enthalpy is 1300 kilojoules per kilogram, velocity is 5 meters per second, and the elevation is 9 meters above our datum, and the outlet of the system, corresponding values include enthalpy of 835 kilojoules per kilogram, outlet velocity 10 meters per second, and the outlet is 35 meters above our datum. If the work done on the system is 435 kilojoules per kilogram of fluid, we've got to calculate the heat transfer and state if a system input or output. Just note from the information stated, the elevation of the inlet is 9 meters from the datum, so Z1 is equal to 9 meters, and the elevation of the outlet, Z2, is 35 meters from the datum. Of course, if you prefer, you could make Z1 equal to 0 and Z2 equals to 26 meters, because it's really the change in elevation or the change in height that we're interested in. Here's a hint. We initially again consider the specific form of the steady flow energy equation, but this time we initially calculate lowercase q. Once we found the heat energy per kilogram, we can find the heat gain per second, uppercase Q, knowing our mass flow rate given in the question, but notice it's in tons per hour, and knowing the Q calculated above. For the information given in the question, you'll find all the terms in the steady flow energy equation are valid to use in this question. I'd encourage you to stop the presentation and attempt example 2, but the full work solution is shown on the following slides. And here's the commencement of the solution to example 2. As always, extract the information from the question. The question wants us to calculate the heat transfer. So in this case, our lowercase q is unknown. The question gives us the mass flow rate of 9 tons per hour. So our m dot is 9 tons per hour, which needs to be converted into kilograms per second. And I'm using two unity brackets here, 1000 kilograms equivalent to 1 ton, and 1 hour equivalent to 3600 seconds. As always, remember these are cancel unity brackets, so we'll cancel the ton here, cancel the hour here, to leave ourselves with a mass flow rate of 2.5 kilograms per second. We're given the inlet enthalpy H1, 1300 kilojoules per kilogram, the outlet enthalpy H2, 835 kilojoules per kilogram, inlet velocity 315 meters per second, and the outlet velocity V2 is 10 meters per second, stated here. We're given height Z1, inlet is 9 meters, elevation of 9 meters stated here, and height Z2 is 35 meters, that's the outlet elevation, 35 meters stated here. We're also given in the question that the work done on the system is 435 kilojoules per kilogram. So lowercase w here, work done on the system, that will be a negative value of work done. Don't forget, work out the system is positive, so work done on the system will be negative. So that's the information extracted from the question. Again, always note that some of the values are in kilojoules, so we need to account for the prefix when undertaking our calculation. Example 2, solution continued. Step 1 here, considering the specific form of the steady flow energy equation, shown here. This time we have to rearrange the equation for lowercase q, so we simply add w to both sides of the equation. Inserting the values from the previous slide and evaluating, lowercase q is approximately equal to negative 89.97 kilojoules per kilogram. Notice the negative value means heat output from the system. Step 2, to find the heat output per second, that's uppercase Q. Uppercase Q is equal to m dot multiplied by lowercase q. So that evaluates to 2.249 times 10 to the 6 joules per second, approximately equal to 2.25 megawatts. I will now leave you with some tutorial questions related to the steady flow energy equation for you to attempt at your own pace. Here's question 1 and question 2. Question 1, you have to calculate the work done. It's shown here, it's a negative work done, so that'll be work done on the system. Question 2, we're asked to calculate the heat lost. Now in mathematical terms, heat loss is a negative value, but because it specifically says loss, that's stated as positive here, 43.4 megawatts. That's the heat lost to the surroundings. I would encourage you to stop the presentation and attempt questions 1 and 2, but I will very briefly show you the full work solutions on the following slides. So here's question 1, commencement of the solution. As always, extract the information from the question. Note in this question it does say it's an adiabatic process, so Q is equal to 0. And we have to calculate the specific work done. The question states that changes in both potential and kinetic energies are negligible. Question 1, solution continued. So we end up with a nice concise formula for work done, essentially the difference between the output and input enthalpy values. Notice the solution is worked through in terms of kilojoules here. It's negative 40 kilojoules per kilogram. So negative means work input to the system, hence the work input W is 40 kilojoules per kilogram. Here's question 2, commencement of the solution. In this question we are given a mass flow rate, it's in kilograms per second, so no need for any conversions. The heat is lost to the surroundings, so that would be Q here, negative 26 kilojoules per kilogram. Given specific enthalpies at inlet and outlet, and we're given the velocity at inlet and velocity at outlet. There's no mention of heights, so we will assume to ignore the potential energy. So Z1 and Z2 are assumed to be 0 in this case. That's the information extracted from the question. Question 2, solution continued. Here's our specific form of the steady flow energy equation, ignoring the potential energy terms here. I have to rearrange for the specific work done W, so again add W to both sides, subtract the enthalpy terms, subtract the kinetic energy terms from both sides. Insert in the values, noting that we have the kilojoules counted for here in our calculations. So evaluating the specific work done is 433.5 kilojoules per kilogram. And finally, working out the power, that's the mass flow rate given in the question, multiplied by the specific work done. So that's 100 kilograms per second, multiplied by the above W value. Your answer for power, actually expressed in 3 different forms here, is essentially 43.35 megawatts. So that's the solution for question 2. Tutorial questions for the steady flow energy equation continued. I'll leave you with question 3 and question 4 to attempt at your own pace. There are no worked solutions for these questions, but the answers are shown here in the brackets. Tutorial questions continued. Question 5, answer is shown here in the bracket. As a hint to help you find the cross-sectional area of the exhaust pipe, you'll need to use this equation and rearrange for A. Note in the equation V2 is the output mean velocity, the italic V2 is the output specific volume. Tutorial questions continued. And here's question 6, question 7, answer stated in the brackets. Here's the bibliography used on which the presentation was based, and I hope this presentation has been of some use to you, and as always, thank you for viewing.